Thank you everyone for tuning into this event. We have a very exciting presentation this evening titled Use of Shaking Table Test in the Seismic Assessment of Nuclear Facilities in the UK. We have two excellent speakers lined up for this evening, and I'm sure you will enjoy listening to them. Let me just tell you briefly about the speakers. We have Adam Crewe, who is a professor of earthquake engineering in the University of Bristol, with over 25 years of experience in using shaking tables for research into the seismic performance of buildings, bridges, soils, and other systems. Recently, he has been leading a major research activity looking at the seismic performance of advanced gas-cooled reactors, core modules using shaking table testing. This research has supported the safety cases for life extension of these older power stations. Adam has also been responsible for the design and execution of hundreds of seismic qualification tests for the nuclear industry, and the recent commissioning of a new high-performance table at Bristol University that can meet the requirements of the latest test codes. Paul Doyle, many of us in the audience might know, is a senior consultant with Jacobs UK Limited, who for many years has been seconded to AWE as Seismic Technical Authority. In the role, he is responsible for reviewing design of structures and mechanical plants subjected to seismic loading, as well as settling standards and providing technical advice on seismic engineering. He has over 40 years of experience, with most of his career in the nuclear and power sector. He is a fellow of Institution of Civil Engineers, Civil and Structural Engineers, and he is also the past chairman of SECOND. I feel very honored to ask Professor Adam Crewe and Paul Doyle to talk us through this fascinating topic on the use of shaking tables in the seismic assessment of nuclear facilities in the UK. If you have any questions, please feel free to use the chat function. If you're asking a question, then please make sure you, so that when I read out the questions in the end, I can know your affiliations. So do mention your affiliations. Over to you, Adam.
Okay, thank you, Chair, ladies and gentlemen. Hopefully you can all briefly see me and hear me. I'm just going to wave because I'm going to switch off my camera in a second as I start this. But I thought, nice to put a name and a face together. So this evening, I'm going to talk about shaking tables and the way they're used in the seismic assessment of nuclear facilities. I'm going to start the sort of first half of the talk focusing on a big research sort of activity that was ongoing at Bristol University, looking at the performance of advanced gas-cooled reactor cores. So these are the AGR cores that are in a lot of old power stations in the UK. And then Paul is going to continue looking at a thing called seismic qualification, which uses shaking tables to test particular specimens. Anyway, so I'm going to start with a little bit about advanced gas-cooled reactor cores. So these have been around a long time. They're a key part of the UK energy supply, but they are now really quite old, and they're essentially operating at or beyond their design life. Now, since they were commissioned, the irradiation in the reactor cores has actually aged the graphite components in them, and that's increased the potential for shrinkage induced cracking. So basically the reactor, the middle of the reactor is starting to shrink and potentially start cracking. Now, it's important that particularly in seismic events, we understand how the core behaves, whether the cracking in the cores is important, whether it's going to potentially affect the safety case for these reactors. So that's the sort of underlying bit of it. And what we were really looking at was the modelling of these reactors in seismic events, and do we actually trust the modelling? So just thinking about that, the modelling that we're using could be a variety of different types. It could be finite element based, it could be discrete element based. There's lots of different models that could be used, ranging from fairly simple models up to really quite complex models. And we need to be sure that they're going to be accurate in the case of the earthquake. And what we were asked to do at Bristol was to have a little bit of a look at this, try and come up with ways of validating these models into regions of operation that people weren't really very sure about. So that's the challenge. And just looking at the cores themselves, it's an incredibly complex contact problem inside these cores. So on the top left, you can just see my mouse there. This is a picture looking down on one of the top of these AGR reactor cores. The larger circles, these are the fuel bricks, so the fuel goes down these columns. The smaller holes in between them are where the control rods go. All of these are graphite components, and then they're keyed together as well, so that the thing can expand and contract as it gets hot and cold during operation. So in a bit more detail, this is a smaller section of it in the middle. You can see, again, the fuel bricks, the control rods columns, and then there's all of these keys that hold the whole thing together. So one of the questions is how do we actually model this accurately? And the first models that were developed looked something like this. So they have a whole load of nonlinear contact springs and dampers between all of the elements. So that was the way the cores were originally modeled. And the question was, how accurate is this? Can we trust these models? Particularly, can we trust these models when there is some damage or cracking inside the reactor? Do we need to update the modelling in any way to be sure that we understand what's going on? So this is an outline of the shaking table test program we were doing at Bristol. The program has actually taken about 10 years. It's just come to the end. So it was about 10 years worth of work to look at various aspects of the behavior of these arrays. And the main thing was to look at the dynamic behavior of the arrays via some physical model testing. And what we were trying to do is work out what's the limits of the validity of the current, or at least of the numerical simulation modeling was, and particularly under a variety of different possible core damage scenarios. So it was looking into the future for where these cores might end up with a little bit of damage inside them, and try and test whether the modeling approaches were actually correct. It was also to try and aim to come up with an assessment of the margin on these. So were the models under or over predicting the performance? And also to look at, sort of just how the behavior of the components changed as we sort of went up to really very large sort of varieties and quantities of damage within the reactor core. So to really push the model beyond probably any reasonable limits of acceptable damage. So the program looked something like this. We started on the left-hand side with some theoretical modeling. I'm going to talk a little bit more about this because there's a bit in here which is to do with scale modeling. And if you haven't been involved with scale modeling, I'll just try and explain some of the complexities of that. So this took a fair bit of time to work out what we were actually going to test, how we were going to do it, how we were going to be sure that the model was actually a good representation of a full-size core. The second phase was to actually build the model, and this was done in 3 different stages. Again, because of the complexity of the model, we wanted really to test it at different levels of complexity to make sure, again, everything was behaving the way we expected. And I'll show you some pictures of those in a second. And then the third phase was actually the shaking table testing. So to do a variety of modal tests, seismic tests, get a lot of data out and use that as evidence in the safety cases to compare, with the models. So the first bit of this worth talking about is scaling and shaking table tests. The challenge here, and this is very, very simplified, but it'll give you an idea of the sort of problem that we have. So just for sake of argument, imagine we have a 1 meter column and we have an area of floor 10 meters by 10 meters by 1 meter thick and a density of 1 for this. So I've got a mass at the top of 100, and if I work out the stress, I've got a stress of 100 units at the bottom. So that's the thing that we would like to model. If I go to a half scale model of this, so not an unreasonable thing to do, the slab goes down to 5 by 5 by half a meter, so it mass drops to 12.5 units. The column is half by half meter, so here is the problem, that the stress now in the material has dropped to 50. So this effectively means that we can't get things like some of the stresses correct in our materials unless we do something a little bit clever when we're doing scaling. And it's not, in this case, I've just looked at stress. We're also interested in, time, velocity, pressures, forces, lots and lots of things that we're interested in as part of this problem. And we're trying to achieve all of them and get them all right at the same time. So there are some ways of dealing with this when we go down to scale models. One of the things we can do is change the material that we're looking at. So if we, for sake of argument, had concrete on the left, we could that was fairly near its ultimate its ultimate strength with a stress of 50, we could try and find another material that was similar to concrete, but was again very close to failure at a stress of 50. So that sort of thing is possible. We could increase gravity. If we actually increased gravity on this one, doubled gravity, our stress would go up. Obviously, increasing gravity can be a little bit tricky, but it is possible within a centrifuge. So there is a way potentially of doing that. Another way of doing it would be to essentially add some extra mass on top of this one. So if we added another 12.5 units of additional mass, that would get the stress up to the correct level. So in more detail, and I'm not expecting you to be able to read this, but these are some of the possible sort of modeling scenarios that can be adopted with shaking table tests, depending on whether you potentially have a shaking table within a centrifuge, whether you decide you're going to model the material, whether you're going to add additional mass, or whether you're going to actually just neglect the issue of the gravity forces. The true model under normal gravity is actually under this column, and this gives you the scaling factors for doing this. So you can see in this case, I haven't scaled gravity. There's a 1 there with the gravity, but I am scaling the length. And the ones that are quite challenging here is things like the Young's modulus and the density that we have to scale proportional to the Young's modulus. And those are really quite difficult to do and make things work at small scale. So the way we did it was to actually come up with a modified true model. So we were scaling the components. In this case, we went down to about quarter scale components, which means that one of these bricks is typically about 300 millimeters high and about 100 millimeters in diameter. So that was the scale, the geometric scaling. And the closest we could come to a representation of graphite, which had an equivalent density and stiffness scaling, was a material called acetyl. This has some significant advantages, that it's very stable with temperature and humidity, and it's relatively easy to machine, particularly to the sort of tolerances we needed, which was down at about sort of 10 micron. So we needed very accurate sort of modeling and of these components, and acetyl allowed us to get fairly close to that. However, it's not an exact model. So the process we adopted for the modeling to the real core was not to try and make an exact model, quarter scale model of the actual graphite core. The way we decided to do it was to start with a quarter scale model. We were then going to do a numerical model of that quarter scale with that acetyl material. That was then going to be converted to, again, a quarter scale model, but just changing the material to the graphite, and then finally going up to the prototype scale, so scaling back up to the full scale. And feeding into this were going to be the material properties, so we actually understood and could compare the physical and numerical models of the quarter scale reactor core. So a bit more looking in detail at the test objectives. We're really using this modelling to validate the numerical models. The original one was a model called G-Core, which was a stick and spring model. Solfac is a 3D discrete element model, and any other models of the cores that we wanted to look at. We wanted to understand the fundamental nonlinear dynamics of the problem. That's a very complex contact rocking problem. We were going to treat the physical model as a prototype in its own right, so we weren't going to try and directly connect this quarter scale directly to the prototype. We were going to go through this loop, just changing one thing at a time. We're also comparing these two models, and therefore gain a much better confidence in our numerical modelling of the whole thing. So once we'd come up with the modelling approach, we then had a phased test programme. This was done largely to reduce the, I suppose, the initial capital cost, to make sure we were actually building the thing, the model properly, and it was going to produce the sort of results we wanted. So we started initially with this thing that we named the mini core, so a relatively small sort of array where we could test potential boundary conditions. We could test various instrumentation solutions, and really try and find out whether we could do this before we invested in a lot of money in components. The second phase was to build a single slice through the model, or through the reactor. So this is the single layer array. So in this case, it's actually sitting on a stainless steel sheet. You can't see that underneath it, but there's a stainless steel sheet, and there's lots of little glass beads to make sure the friction is as low as possible. This allowed us to really look at how the core behaved in an earthquake, so we could shake this. We could test out various types of instrumentation, again on this array, and particularly some of the camera systems I'm going to talk about in a second. And then the third, and really the production testing, was done with a thing called the MLA, so a multi-layer array. So this was 8 layers deep and 20 bricks across the diameter. We had a lot of instrumentation inside it, camera systems looking at the top, and we were able to shake this thousands of times with various different crack arrangements in it to look at the performance of the core. So the MLA specimen in a little bit more detail. It's got about 40,000 components in it, so one of the biggest jigsaw pieces or puzzles ever. It took about 2 months for 2 people to put together. So quite a complex thing to get right, particularly when it had cracked components inside it. When it's intact, there weren't so many different components, but when it had a significant number of cracked bricks inside it, very challenging to put together. It had, by the end of the test program, over 3,000 sensors inside it, which we believe is the most sensors ever attempted on any shaking table test. It's just say it's most people wouldn't want to go more than sort of a few hundred sensors. So there was a big challenge in that, just to get the instrumentation in. And the whole thing was about 2.5 by 2.5 by 2 meters in size. So I've mentioned instrumentation. This really was a challenge and took quite a lot of the team's time to really to get right, to make sure it was accurate enough to give us really high quality data for comparison with the numerical modeling, a system that was robust enough that could be shaken many times at potentially very high acceleration levels. Ideally, we would have liked to buy something, but that was completely impossible. No one had attempted to put the sorts of types of instrumentation in any shaking table test that we needed. So, for example, in the on this one, on actually no, I'll talk about the fuel bricks. This is the simplest of them. So the fuel bricks are quite large. They have quite a lot of there's quite a lot of volume to them, and the way these are keyed together, they're only able to rock, and they can't slide up their bases. So in this case, it was quite easy to work out how they were rocking on top of each other just by putting 4 LVDTs. So you can see one of them sitting out here, sticking out of the bottom of each brick onto the top interface of the next brick. By having 4 sensors, that allowed a little bit of redundancy if one went wrong, but 3 sensors allows you to get the 3 degrees of freedom in rocking. So that was fairly straightforward. The more of the challenge was in the control rod columns, because these interfaces, this is only one part of them with a filler brick, but they have an annular ring around them. The brick on top has essentially a keyway that fits onto that, but there is clearance around the edge, so it's possible for this particular interface to move in all 6 degrees of freedom. So it can rotate, but it can also slide, and it can potentially jump up and down a little bit. We weren't able to put these sorts of LVDTs in this interface because anything that we really put in there was going to affect the dynamics of that interface, and there are 12, 13 of them up one of the columns in our test specimen. So if we have anything that is sprung, it will start affecting the dynamics. Also, having any cables running between them is again adding additional stiffness. So a real challenge here. The way we solved the problem was to use Hall effect transducers. You can see these small little microchips just about on each of these 3 corners. So each of these chips has 2 sensors in it. So there is 4 in each of the corners. So a total of 12 sensors, which is more than the 6 degrees of freedom that we're trying to measure. So we can actually calculate all of the motion of these interfaces. On the brick above this, there are some magnets, and what we're essentially doing is measuring the distance of the magnets from those sensors. It sounds, when I put it like that, actually quite simple to do, but and 4 Hall effect sensors are incredibly non-linear. So the calibration process of this was really very challenging. I've got some references at the end if you want to look into this in more detail. The sensors then couldn't be collected via conventional data acquisition system because that so many wires would have affected the dynamics. So we developed our own custom data acquisition boards that essentially slotted into the bricks, and then actually you can maybe just see one there, but there is a little grey ribbon cable that basically daisy chains these up the column. So very, very little in the way of cabling between the sensors to avoid problems with our instrumentation affecting the dynamics. So in total, we've got, as I said, about 44,000 components to do one lattice column, and to get the column profile, we need 82 sensors. So that's 4 of those per interface. We also have accelerometers in there, which is why it looks a little bit higher. For the control rod columns, we have to have 195 sensors. And then we had also some monitoring of keys and cracked bricks, leading us to about, over 3,000 sensors in the array at the end. We were doing about 500 tests per configuration, and that was producing around about 1.5 terabytes of data for each configuration that we tested. So other things we were doing, that was, I've shown you the basic instrumentation. We also developed some infrared and high-speed camera systems and deployed those on the array. So around, this is the single layer on the shaking table, but you can see we have a frame around the outside, a whole load of cameras, 5 infrared cameras, which are in red, and then 1 high-speed video camera that looks directly down on the array. The infrared cameras are the sorts of things that are used on a lot of film studios with the green screen. They have little silver reflective spheres. We use much smaller ones than are used in the film studios, and by putting 3 of these on the top of a brick, we could work out where the center of the brick is, and therefore we could track the centroids of these bricks. And as I said, this worked. This tracking system was down at about 0.1, 0.2 mil accuracy. So that's dynamic accuracy. The high-speed video the one problem with this is there was a limit to how many sensors we could actually sensibly put onto the top of the array. So that was why this system was slightly limited and we couldn't track absolutely everything. So we combined it with a high-speed video camera system and then used motion tracking to try and track more of the top of the array. So what we were able to do with this system was to track things like keys. So here you can see on the left-hand side, we've got some templates on a black background of the things we want to track. So in this case, our software has picked up the keys, and you can see in the main picture, all of the keys have been picked up, which are all of these little sort of red triangles where the software has identified a key. And then from frame to frame, we would look at where all the keys were, and that would allow us to produce plots like this one on the bottom, which shows the relative displacements of various components. We were also able, as I said, with the infrared camera and the infrared markers, to watch things like a cracked brick that you can see here. So 3 on each of the markers on each side of the cracked brick, and allow us to see what was going on and look at the separations between these. Different templates allowed us to do different types of monitoring. So you can see here we're picking up the keys. By using an interstitial slice, we could pick up the interstitial columns in the whole array. And then again, sort of half bricks, we could in this case pick up damaged components. You probably spotted that the fuel bricks are actually black and quite difficult to see. So again, a trick we discovered sort of halfway through was actually to invert the high-speed video image, and then the black becomes white, and we were able to pick up, as you can see in this one, all of the fuel bricks and track those. So this was a very powerful way of monitoring the components. Unfortunately, it does depend on the camera resolution, and in this case, we managed to track at about 0.5 millimeter accuracy. So not quite as good as the infrared system, but it did give us full field coverage of the entire array. So with this sort of information, we could post-process all of the video data. We could produce plots like this that shows how at various times during one of the shakes, the top of the array was behaving. In this case, not completely symmetrically, but you can see the patterns. There's a sort of a sloshing to the left. We then get some sort of interesting, almost sort of little vortices in there, and then it sort of comes round to the right. So allows us to really get a bit of a feel for what's going on inside the model. And this was the sort of data that was compared with one of the modeling approaches. So in this case, G-core, which is the stick spring model. So you can see sort of typical data at the bottom where the specimen is in red and the G-core, the model, is in blue, and they're looking pretty good. We also actually here you can just see where we've used some of the infrared markers on the keys to try and look at the way the keys were behaving. One question relatively early on was, if one of these bricks break, where do the keys go in the model? So trying to track the keys and understand where they disappear to was very important. It was also possible, with all of the tracking we were doing on the top of the array, to look at where the peak displacements were. So over the process of a time history, what did the peak relative displacement of the array look like? And again, you can see, that for, in this case, 4 different levels of input. So this is a relatively low level, 20% of the main test history, relatively little motion in the middle. Once we get up to 100%, we've got a lot more motion, but interestingly, at 140%, we're not getting significantly more motion of the array. So it is at that point, been limited by the tolerances and the gaps between the components that exist. The instrumentation that we had in the middle of the array allowed us to work out the column distortions, which was particularly important because the concern is, will the control rods go down into the array in the case of a seismic event? So the way we were doing this, as I showed you earlier, was to look at each of the interface motions, so either 3 or 6 degree of freedom, depending on what we were looking at. So we're looking at each of those interface motions, and we then did a fairly complex process of integrating these motions up the column. So we looked at the relative interface of each of these up the array, and built up the distortion profile. And this is sort of typical of the sorts of results we can get. So in purple is the test specimen, and in green is the G-core model. Once we started seeing results like this, we were actually able to look at the modeling in a lot more detail, start questioning whether the model was actually a good representation of the core. And over the years, there were quite a lot of updates to the modeling based on the experiment. So particularly some of the things that were actually in the physical model weren't represented as well as they could have been in the G-core model. So by updating that, we were able to get much closer results. It was also possible to produce some animations of this data. So this on the left, you can see in this case the rig in black, and Solfec, which is one of the discrete element codes, and a comparison between those during the shake. And again, pretty good agreement between those. I'll just get this other video going. And this is some of the output from that, some of the Solfec modeling. So this is solid modeling, software, and you can see, I'll run it again, but just have a look at the key in the middle, because you can see the sort of contact problem that we've got in there. So the key sort of rotates, jams a little bit between the various components. And this is why I was saying it actually a very difficult problem to model accurately, where you've got these sort of really complex distortions. Another advantage of having a physical model is that at the end of testing you can actually have a look at it. So we at the end of the testing we did a lot of camera inspection. So this is at the one of the views on the left hand side, looking down the top of one of the fuel columns. They are the white and the black, deliberately different colors, so you can see cracked bricks, and you can see in this case one of these keys has actually moved into the crack and essentially jammed that brick slightly further open. One of the concerns was if too many of these keys go through into the control rods, they could actually jam against the fuel, and that might mean that the fuel rods could not be withdrawn sort of after a shake, which wouldn't be very good. Another thing you could see from the top of the array is columns sometimes like this, because all of these keys were supported basically one on top of each other all the way down through the array. So this is the left and right is what it should look like with the keys all the way up to the top. Here we've clearly lost keys. The keys were all numbered, and when we did forensic dismantles at the end, we actually worked out where all of these keys had gone. So we were looking to try and really understand what had happened during the shaking. Some other things we were doing was looking at the forces that were being imposed on the keyways. So again, this is some of our prototype sort of testing arrangements. So how we were going to measure a keyway in here or a key in there, which might be sort of shearing or jamming or rotating, and through this actually relatively simple arrangement of a couple of beam load cells, we could see that you can actually get quite different behaviors from the keys within the array. So the loose keys would tend to rotate and jam, so you get forces on both of the load cells at the same time, whereas the integral keys, which are fixed rigidly to the interstitial columns, these ones tended to move and just sort of shear and hit one side or the other. So you would either see one of these or the other side actually with a force in them. So quite a lot of quite complex instrumentation being developed. The final aspect that we looked at as part of the test program was what would happen if one of the bricks actually broke during a shake. Now, if you remember back to the start, I was talking about modeling of the bricks and getting the right materials. We used the C tool. It's robust, it's easy to machine and make nicely and accurately, but it's by being robust, it doesn't break during any of the shakes that we can put into it. So what we had to do was try and develop a brick that it could essentially break under some sort of control. And this was the final way we came up with doing it. So a custom load cell sat in one half of a broken or a pre-broken brick. In the other side, there was an electromagnet, and then integrated, sort of data acquisition system, microcontroller that controlled the electromagnet. So we measured the loads in the load cell in real time, checked what those forces were, and when they had exceeded some predefined force, then the electromagnet was released and the brick essentially broke in half. And that's allowed us to test, as I said, what would happen with sort of damage during the shake. The first bit of modelling, so the original modelling that was being done on the reactor core, couldn't cope with real-time damage. Towards the end of the project, software was developed that could actually look at the data, and we could compare with the data that we were producing. And the sorts of things that we were seeing is that, yes, there is clearly a change in the behavior of the array when bricks sort of are artificially cracked, and there is sort of local differences in response, but generally there's no overall change in the array. Whether the crack is there or not in the way at the start, with respect to the sort of peak behavior of the array, and that's pretty good because it really simplifies the modelling of the reactor cores. So the key outcomes from this work, is that close correlation between the experiment and the simulation. And we got a huge amount of qualitative and quantitative sort of information about the way one of these cores actually behaves. We got it led to significant improvements and much greater confidence in the numerical models, which were used to underpin the safety case arguments for these stations. We reckon that it's allowed the EDF to keep the power stations on for around about 4 years beyond their original planned shutdown dates, which is terawatt days of generation. So a huge amount of energy has been produced because of this work. And similar sorts of programs could actually be used to develop other help solve the problems of other modelling challenges within the nuclear sector. So I mentioned that there's if you want more data on some of these things, take a screenshot of that. There are a lot of papers out there that talk about the work that we've been done. So please go and look at more, or equally get in touch with me if you want to find out more about what we've been doing. So I'm now going to hand over to Paul, who's going to talk about a slightly different use of shaking tables. These are some pictures of equipment qualification we've done at Bristol. So the graphite program was really all to do with the modelling and do we trust the modelling? And in some respects, this is similar. But rather than testing smaller models, we're actually going to test the full-size equipment. So I'm not going to, I won't say more about this, and I'll just hand you over to Paul now.
Today I wanted to talk about the use we're making of shaking tables at AWE for qualifying equipment. I wanted to talk about, what happens from the client's perspective, how you go about specifying the table testing, and then I want to give some examples of what we've been doing, and concluding with their use in nuclear safety case. As we've just seen from Adam, many systems are very, very complex. They can be amenable to linear analysis, and that is great. Some require non-linear analysis. However, what do you do when the nonlinearity is very complex? Or what do you do when the function that is very important? You want to make certain a piece of equipment is going to work before, during, and after the earthquake. You might want to do this from filters and valves in the containment system. You want to be using mechanical equipment, which often relies on non-backdriving gearbox to support the load. But how well does that work in an earthquake? There are two ways that you can use this. One is the use of experience data, such as the SQUG database. But that only works if you've got appropriate examples. The other way forward is by shake table testing, a subject of our talk tonight. It's not as simple for shake table testing as just saying, oh, I want to do a shake table test, and there's a lot of work and preparation that you need to do before you can actually start the shake table testing. Sorry, my screen suddenly jumped. Before you can start, you've got to think, what is it you want to be tested? It sounds a very simple question, but you may have a very complex piece of equipment. For example, a filter bank. Do you want to test the whole filter bank? Do you want to test an individual filter? How's it going to be supported? The piece of equipment may be part way up the building. It may be supported by other secondary steelwork. What are you going to say is an acceptable test? What sort of levels of instrumentation do you need? Where do you want to know your accelerations and displacements? And what other measurements are needed? The output from some of those we just heard from in Adam's talk, but I'll have to talk some other examples. And the final bit you need to think about is, what is the input spectrum you're going to use? If the piece of equipment is on secondary or tertiary steelwork, you may need to do separate analyses to determine what the appropriate spectra is. Damping is a question that often arises when you're using the spectra, but for the shake table testing, the equipment converts a spectrum into an input acceleration, and your damping, it doesn't actually matter in that case, as long as you're consistent. The damping for your spectra and the damping for the table are consistent. And you also need to follow the various code requirements I'll talk about on my next slide. In practice, this little bit of information here, there is often as much work goes into preparing for the table testing as in actually doing the table testing. For nuclear work, we always like to have codes to use. For structures, the ASC, the American Society of Civil Engineering, code 43 is one of the ones that's used, but it's also applicable to mechanical plant as well. In one of their sections, they talk about the different types of shake table testing you can do. A proof test, where you're taking just a single test and the required response spectra. Or a fragility test, where you're looking to see what happens as you gradually increase the earthquake levels you're subjecting it to. The basic requirements for testing, what's acceptable spectra a matching of between the table spectra and the input spectra, and various other parameters such as that are given by IEE 344. That surprisingly is an electrical standard which was originally developed for testing electrical equipment, but it's equally applicable for any structural or mechanical work. One of the things that ASC 43 addresses is what happens to make certain that the single test is reliable enough to give the performance goals you require. To do this, you need to put a factor of 1.33 on the required spectra as the input spectra. I now want to talk about some of the examples of equipment qualification from AWE's work. I want to talk about the qualification of some sintered metal HEPA filters, various valves for a safety system, and a waste drum stack. Sintered metal filters, a high pressure, high temperature metal filter is capable of working in very extreme conditions. The safety functional requirement was to be able to filter the air to very high standards. You're typically talking of 1/10,000th of the particles in the air being transmitted. Now, the fact of any small holes in the filter mesh very drastically reduces the performance of the filters. But you can't really check on that by analysis. It's just how the filter mesh behaves in an earthquake. We did this by testing the performance of the filter both before and after the earthquake. Fortunately for this particular application, we didn't need to maintain the performance during the earthquake. We had two different testing campaigns for the two different types of filters. Fortunately, there were very different spectra that was on them. We had quite a large filter, about 2 meter high unit, and a small pipe-based filter, which is much smaller unit. In both cases, the shake table testing was successfully demonstrated that everything was adequate. The second example I want to show is for a safety system where we had air circulating and the valves need to perform in a predictable manner. The safety function requirement was that the valves had to continue to perform after the earthquake without inspection. Some of the valves were closed and must remain sealed, and some of the open valves must remain open. You can see from the photograph, there's a number of different valves we tested, complete with their actuating mechanisms, and they're all put onto a single rig to enable sort of 5 valves to be tested simultaneously. The assumption was made that the valves would be in their default operating mode with no power applied. Again, during the earthquake, we can't guarantee there's going to be power. So the system was designed such that power wasn't needed to maintain the normal state. Analysis can be used to determine the strength of the valve with no problem at all, very conventional. But what actually happens to the sealing and actuating mechanism? How does that perform during the earthquake? Does it carry on performing as you want to do? So in this case, the testing again was successful and demonstrated that the valves continue to perform. Now I'm about to move on to my final example. As many nuclear operators have, we had huge amounts of waste stored in drums. This waste was stored in racks up to 5 high. The safety case required, because some of the drums could be heavily contaminated, it had to withstand a 10⁻⁴ earthquake. The geometry of the frames was complex, designed for forklift truck handling, with 4 corner posts and a base plate, with the frames stacked one on top of the other. In the bottom of the frame, you can see there's a sort of cone arrangement, and that it interlocks with the level below. No other restraint was available. So we decided to test at full scale a stack of drums. When you see an individual stack of drums, sort of the height ratio, it looks relatively unstable. So a great concern was to make certain that we didn't know if these drums were going to topple or not. So a number of safety mechanisms had to be incorporated into the testing. There is a rope that winds its way through the legs and held from the rig at the top, so that generally the frames overall can't collapse, but the rope would restrain them. There was also concern whether an individual drum could come out of the frame, so sort of netting was put there as a temporary process. The testing was done in increments, starting at 25% of the earthquake, eventually moving up 25, 20, 50, 75, 100, and then the final test was 125%. So I'll show you now the testing. See the severe non-linear behaviour of the drums. I'll show that video again. Movement occurring on the cone feet, the drums hitting the uprights, but everything remained stable and just as we wanted it to behave. Having achieved the rating we wanted to, we then decided to do further testing without the netting present. So the netting was removed and the testing was repeated to see if the netting was causing the problem, any additional restraint. So I'll show you now that. Sorry, I pressed the wrong key. So again, very similar response to with the netting. I'll show that one again. So concluding, shake table testing has been very helpful to us in demonstrating the safety functions can be satisfied. The reports we get back from the testing are often very extensive, And so therefore we've often had to produce summary reports to show how everything's achieved. ASC 43 has been useful to help us to demonstrate that we get adequate reliability from a single test. The conclusions have also been have now been accepted by our nuclear regulator, ONR, as a way forward of demonstrating the work. Thank you everybody for listening. If there are any questions now, we'd both be pleased to address them. You could type them into the question box.
Thank you for the presentation, excellent presentation, Adam and Paul. I'll just urge the audience, if you have any questions, please type them in the chat box so that we can have our speakers responding to them. I think there is a question from Zehad Khalil from Imperial College. It's a very long question, Adam. I can just try and read it. There's several parts of the question, so I'm just going to read part by part and you can respond. So what is the first thing is that saying it's not really clear what are the main performance criteria for assessment. Is it only core integrity, containment, or others? Maybe you can take that first and then we can do one by one.
Okay, well, thank you very much for this quite complex question that I can see. A lot of this is to do with the modelling, and at this point I should point out that the bit of the work we were doing in Bristol was mainly, but not exclusively, but mainly focused on the experimental side of the testing, and colleagues in Atkins were more responsible for the for the GCORE models, and other universities were responsible for things like the Solfec model. So there were actually a lot of people involved with this. I think your question is actually really referring to the safety case itself, which in Bristol we were not directly involved with. So core integrity, containment, I mean, in the safety case, it's all of those. From the testing of what we were doing, we were not really worried so much about how the specimen failed, but just recording what happened and then comparing it with the model. So I'm not sure whether that, I'm hoping that sort of answers your question. Shall I go on and read the next bits?
Yeah, I can just get it. How did you model crack propagation under the seismic load numerically?
So for that one, we didn't. That was part of Atkins and other people who were involved with the safety cases. I believe they were doing it with very detailed FE modelling of the specific bricks, and I think that was backed up with some experimental work. But again, we weren't involved with either of those aspects.
So the other parts of the question, if you read further, they are also related to the numerical modeling, actually.
Yes, I mean, then there was one about cracking during the seismic event. Well, that was the bit we were looking at, with the what we were calling the crack on demand bricks. So, I mean, the how did we expect the cracking to progress? Well, it would, if there was a crack, it would move, go from where there was some sort of crack initiated, and it would be a very sudden event. Different ones of the models that I have seen, actually looked at those crack propagations and the energy releases in them, but again, it wasn't something we were specifically looking at. There's a bit of the question on the interaction with the other components, which is that one, it does relate to the experimental work. We did not model the fuel rods or the control rods within the shaking table tests. It was something that we did consider a few years into the program of work, whether we could actually model those actually within the experiment. Potentially it was doable. They would have been very hard to instrument. For the fuel rods, they've actually got a reasonable amount of clearance. So it was the modelling has suggested that even if the columns distort, they won't actually impact and cause any damage to the fuel rods. So it wasn't felt to be a sort of a high risk problem. The control rods dropping in, there's other experiments which have actually looked at that problem at full scale. So with distorted control rod columns and doing real-time drops of the articulated control rods into them. So again, it wasn't something that was considered essential for our work. The final part of the question was asking about time aging effect regarding the change of geometry, strength, and how that was captured. Well, the change in geometry, our model is built at a 34 full power year dimensions. So that was taken into account right at the very start. The reduced strength, we haven't modelled that, which is why we can't actually have we don't have the bricks themselves cracking. We were looking at the bricks were either pre-cracked and built like that, or they were intact. Hope that answers the question.
Thank you for such a detailed response. I will move on to the next question, which is for Paul. Actually, this question is from Ian Stone from Cavendish Nuclear. The question that he's asking is: was there a requirement to test for the effects of adjacent drum stacks interacting with each other during a seismic event?
It wasn't something we addressed directly in the testing. The argument was put together that the interaction between the drums wouldn't cause an increase in stability. We were primarily concerned with making certain the drum stack as a whole remained together. Ideally, we should have looked at it further, but we didn't.
Okay, thank you. The next question is from Leslie Simpson from Cavendish Nuclear again. So the question reads as: within the UK, is the greatest limitation in shaker table testing the physical size? Is model scale generally not carried out in industry due to the constraints outlined by Adam? So I guess, Adam, probably you can take this question.
Okay, I mean, yes, producing scale models is challenging. Actually doing tests at full scale is equally challenging. As Paul has pointed out, there are just sort of different types of problem. I think the key thing is that the tests have got to be designed appropriately to get the relevant information out of them. So doing small scale testing isn't necessarily a bad idea, because there are things that you can do at small scale that just become impractical at large scale. The shaking table we've got at Bristol the one we did these tests on is a sort of smallish table, 3 by 3 meters. We do now have a new shaking table at Bristol, which is 6 by 4 with a much bigger capacity of 50 tons. If we had that at the time, we would probably have used that table. I doubt we would have wanted to test the model much bigger anyhow, simply because the number of components was already fairly significant, and the cost of materials and actually making the specimen would have got in the way of actually doing the work. So it's a balance. Test what you have to at full size, and if you don't have to do it at full size and you can do a small scale test, try and do a smaller scale test.
Paul, do you want to add anything to this response?
So the next, no, I don't think there's really anything I can say. For our particular problem, it's easy to do it at full scale because we're within the table capacity.
Okay, the next question is for you, Paul. It's from Colin Morrison, and he is saying that 1.25 margin in incremental testing of drums, vs 1.33 for single test. Is this from ASC 43? I think.
Yeah, I wanted to show that the videos, we're comparing them with the two at 125%, the margin of 25%. So I omitted to mention that the first test, when we still got the netting on, we did actually do it 40% above the design earthquake. So,
thank you. Thank you.
Yep.
The next question is from Joe Joyner from, again, Cavendish. This says, does ASC 43 and IEEE 344 define factors such as test duration, 10 seconds seems quite short, method to derive the table motion from SRS, and number of different input motion tests required? Is the table motion derived using software from SRS input?
There's a number of questions there. The test duration, the normally accepted length for the UK earthquake is about 12 seconds. And that is what we used for the testing. The video may have lasted a bit less because there's very little motion appearing at sort of the tail end. I probably clipped it a bit too much for this presentation. The input motion is we define the spectra in all three directions. Then Adam's very sophisticated software converts that spectrum into an acceleration for each of the three directions. So it's a bit like it's a time history approach. So you don't need to worry about SRSS or anything like that. I don't know if Adam would like to explain a bit more on that aspect.
Thank you. Do you want to add anything to this response, Adam, before we move to the next question?
I think probably I'd probably have to spend too long going into more detail. I mean, we start with spectra and generate time histories that contain the relevant amount of energy with that spectra. Also trying to match the time duration and the sort of envelope of the time history. So we can basically generate artificial earthquakes that will meet any test spectra.
Thank you for the response. We have a question from Zubair Vani. I think if he's joining from NIT Srinagar, it's quite late there, so very impressed that people from India have joined this talk. But the question, this is, I think, more like, could you share some literature on model scaling? It would help very much early researchers in this field.
Yeah, absolutely. There is one key book that I would recommend. So I haven't found it. Oh no, I have got an ISBN number if that would help. But the one I would recommend, it's called Structural Modeling and Experimental Techniques. So Structural Modeling and Experimental Techniques. It's by Harris and Sabnis, Sabnis. And I've got a very long ISBN number, which I hope is correct, which is 978 084 932 4697. And that goes through modeling, lots of different types of structural modeling for shaking table work, but also centrifuges, things like that. Highly recommended book. Sorry it's so expensive though.
Thank you very much. I do not see any more questions. There's one question I would like to just ask Paul, because you mentioned that this also you got from ONR. Did you have a what sort of process did you follow to get because normally with any type of physical testing, it's quite hard to kind of get agreement, and there are lots of questions. Was it a very, what can you just explain the process? Was it a very difficult process to get ONR to expect these results, to kind of take these results from the physical testing? Yes.
I wasn't directly involved with the process myself, but I understand we had very little questions on it, actually.
Because it becomes quite difficult to try and get
Yeah.
agreement, and it's a long process. There's just one thing, last thing. I think if there are no further questions, then probably we can draw this session to a close. I would like to thank our speakers for this evening, Adam and Paul, for giving excellent presentation and showing something really remarkable for people who are using physical testing. And I am just going to kind of, before we finish, I'm just going to show what our next talk is going to be, so that you can all mark your diaries for the next second talk. The next second talk is actually on the 30th of March, which is again the last Wednesday of March. And the interesting thing is we are planning and hoping that we will be back in ICE. So this is going to be an event. This will be a chance for you to catch up with colleagues. We've been doing online for a while now, so this event is going to be, of course, it will also be transmitted. It will be a hybrid event, but we would all love to see most of our second members at ICE for this talk. The talk this is on designing for seismic safety and resilience. This will cover Asian Development Bank project, which is also called as Pipeline to Prosperity in Dhaka in Bangladesh. This project is under construction at the moment, and some of the challenges and features will be shared in this talk. With that, I will draw. I hope we can all give a virtual clap. And unfortunately, we can't take you for a drink now. But thank you very much for your time and for tuning into Second Events. Keep supporting Seconds. Thank you, everyone.